Hello, everyone. Today we present Lambda Learner, a method to incrementally learn personalization models using streams of data. This work is done and influenced by many teams at LinkedIn, and we are presenting this work on their behalf. I'm Rohan, and with me are my co-presenters, Jeff and Konstantin, and you will hear from them shortly after. Although we are going to talk about near real-time personalized models that can generically apply to most recommender systems, we're going to ground the application in LinkedIn ads, or sponsored updates as we call it. Here, the task is to predict the click-through rate of an ad given a member's browsing context. These are the ads that you might have seen on your LinkedIn feed. It could be just plain text, an image, a video, a form, or even a carousel. This is a fairly large-scale machine learning problem. To understand some of the motivation behind our design choices, we should ground this in the scale of the problem. We process about 10 terabytes of data per model and run about 50 machine learning A/B tests simultaneously. We use almost the entire LinkedIn economic graph with about 50 billion edges and 1 billion nodes to extract some of the features we use in the model. Most models used for recommender systems can be broken up into two components, where the first part is the one that contributes to the generalization performance on unseen data. Embedding-based models and deep learning models are good examples of this kind. And a part that is responsible for memorization. These models achieve hyper-personalization using entities in the historical data. Interaction features and ID features are good examples of this. Now, these memorization features are both transient and ever-growing. So updating this part of the model fast is critical to performance. And that is the focus of this talk. To understand why this is important, think of a situation where an advertiser comes in and creates a new advertising campaign. This campaign can now reach thousands of impressions in a few minutes. Similarly, a job posting can reach millions of job seekers in a short amount of time. In these cases, recommendation models need to learn from the information as quickly as possible. The model we use at LinkedIn, we call a generalized additive mixed effect model. It's essentially an ensemble where we have a global model, which is either based on deep learning or uses embeddings or some form of nonlinear models. And then we have a large number of small models that are boosted over this global model. And these large number of small models are what we call the random effect models. Now, these random effect models are responsible for memorization. They're trained on the residual of the global model score. And the best part is they only depend on the data corresponding to each entity. What that means is when I'm training the model for one advertiser, I only need to use the information about this advertiser and all of their interactions in the past. So far, I've explained that memorization models are important. They need to be trained as fast as possible and what the model looks like. Let us now dive into what it takes for us to train them fast. These random effect models are characterized by three important properties. The data per entity is ever growing, so we cannot hold all of it in memory. Model training is inherently parallelizable. What that means is if I'm training models corresponding to two different advertisers, they both can be independently trained since they depend on different data sources. And model updates are asynchronous. Again, what that means is assume we have a large advertiser that gets a lot of impressions. So the number of times we trigger the model update for this advertiser will be far larger than a smaller advertiser. And that is okay. We don't need to update all advertisers' models simultaneously. Now, because we want to train using streams of data, we modify the loss function. Instead of using the typical batch loss function, we use a time discounted cumulative loss, where if omega t is the mini batch of data that we want to train on, then ft is the loss at mini batch t. Now, the overall loss function, which is denoted by capital F, is then an aggregation across all of the mini batches where older mini batches get discounted and newer mini batches get a higher weight in the loss function. What this means in practice is we're saying the more recent the data is, the more important it is for our model to learn from. And by setting a value of delta less than 1, we end up discounting older batches of data. Now, if you look at this loss function, there is still a problem, right? This loss function still depends on all of the data from time 0 through time t, because the term ft minus 1 is indirectly a way to bring in all of the data. Now, this still requires us to hold all the data in memory for us to iterate on these models. So let's see how we can address that. We first begin by assuming there is a Gaussian prior over our model parameters. When we add this prior to the loss function, we get a new loss function that now still depends on ft minus 1, but it has an additional prior term. Since we use the log logistic loss function, a Gaussian prior means that the posterior is also going to be Gaussian. We'll see how this is important later. Although this still depends on the historical data indirectly through ft minus 1, we can now introduce an approximation. We approximate this function using a quadratic function that is centered around the previous optimum, beta t minus 1, to get a new loss function now. As you see, this function only depends on the current mini batch of data and the solution up to the previous mini batch. We don't need all of the data from time 0 through time t minus 1 anymore. And this way, we can train just on the mini batch of data as long as we know the previous solution. What this means in a Bayesian context is this is equivalent to using the posterior of time t minus 1 as the prior to compute the parameters for time step t. As I mentioned, the update only depends on the previous solution and the current mini batch. Now, since the posterior is also Gaussian, the posterior covariance is also available in the output. This system now behaves like an online contextual bandit via Thompson sampling, where you can understand this by the system estimates the value of each arm of the bandit much faster because of a fast feedback loop. So there is another application for this system in reinforcement learning. So far, we've described the motivation, the problem, and a theoretical framework to solve it. Jeff will now walk us through what it takes to build this in practice.
Thanks, Rohan. We deploy incremental learning in production with expectation of improvements along multiple fronts. Number one, we expect to reduce the effect of cold start in our system. This is due to the fact that with incremental training, we're able to deploy random effect models learned on newly observed entities with very little delay. In the context of ad serving, this includes new advertisers, newly published advertisements, and new LinkedIn members. The same applies to returning entities that may have been dormant for the duration of our training window. Secondly, we expect to better respond to data shifts. Data shifts occur when new patterns are introduced for specific entities. Shifts can be triggered externally, such as by something like a current event, or by a change of internal behavior on our website, such as a member changing his city of residence. To address these problems within our advertising platform, we built a nearline infrastructure, which I'll walk you through now. Our nearline infrastructure is dependent on three major components, which are built atop a variety of technologies, many of them open sourced. The first is a streaming data producer, which combines front-end and back-end tracking events to produce training data. This is powered by Apache Kafka, a distributed messaging system, and Apache Samza, which is a stream processing framework. The next component is a scalable key value store. The goal of the key value store is to maintain a shared state of our random effect models. This is critical for asynchronous updating as well as offline recalibration, which I'll talk about later in the presentation. Last is our offline global model. Random effect models are trained on the residuals of a generalized global model. And in our case, we train these global models using Apache Spark. Let's go deeper into the first component, the streaming data processor. The goal of incremental learning is to reduce the time between member action and knowledge deployment. One of the largest bottlenecks in this process is the production of training data. In order to address this, we emit all feature values used to make predictions in real time from our service. We do this using Apache Kafka. This enables us to skip very large offline joins while also allowing us to capture correct feature states for all of our predictions. We then leverage Apache Samza to produce string joins between our feature tracking topics and front-end interaction topics. In practice, one of the biggest challenges is accurately determining from streams how long to wait for positive interactions after an impression. This is ultimately an availability versus recall trade-off, and in our case, we used heuristics so that we could capture 95% of our positive interactions. After performing the join, we again use the Kafka topic to publish our output. However, at this time, we've published a complete training example. Since random effect models still require the prediction of the global model, in our next step, we use an additional stream processing component that consumes the training data topic and produces the same object with the additional global offset. The global model itself can be trained and deployed independently of our nearline infrastructure. One question might be, why don't we include our global offsets in our feature tracking? This is certainly possible, but in an environment like LinkedIn that does a lot of A/B testing, there are many global model variants that may be used to serve incoming traffic. And in this step, we're pretty much consolidating them and guaranteeing uniformity. Lastly, we have a final stream processor that groups training examples by their respective entity IDs. When a window of data is gathered for a particular ID, our processor interfaces with our key value store to fetch the current state of an ID's random effect coefficients and performs the incremental update that Rohan presented earlier. After the incremental update is completed, the processor pushes the new coefficients to the same key value store. As data stream velocity fluctuates throughout a day, what defines a sufficient window of data can be a variety of things. One could be the number of collected training examples for a given ID. Another could be the time since the last update of an ID. And the third one could be sort of the variance of the data under an ID. It is important to mention that each random effect model is independent of one another. So each ID can be updated asynchronously. Finally, our online services use the key value store to make predictions on incoming traffic. Some of the additional considerations that have gone into our system are: 1, recalibration. Over time, the compounding effects of label inaccuracy and quadratic approximation causes the model to diverge from its offline counterpart. Therefore, in regular intervals, we found that it helps to redeploy models that we've trained offline. 2, the time discount factor and hyperparameter tuning. When dealing with hyperparameters, such as our time discount factor, we really realized that optimal values were often domain specific. Therefore, we built an offline framework to chronologically replay the inputs to our system. This allows us to tune hyperparameters and conduct accurate experiments. Kostya will now talk about those experiments as well as the results of our production deployment.
Thanks, Jeff. Hello, everyone. I'll first describe our offline results. We use sliding window over data to simulate and replay the online stream. We use 2 weeks of sponsored updates as our data set. This is a private data set, but for reproducibility, in the paper, we also report the results on a publicly available data. The area under row curve is our offline evaluation metric, and we evaluate against the batch algorithm analyzing the impact of update frequency and the cost of training. We evaluate Lambda learner against 3 batch variants that differ in what data is available to them, visualized in this diagram. Left to right is the time. The leftmost data segment here is available to all the variants, and it is used for initialization. For example, it is used to train the first batch model, and it is also used to train the first prior of the Lambda learner. The rightmost segment is used for evaluation also by all the models. The middle segment is where the variants differ. Let's go over them one by one. The first one is a batch model that is not updated, and it's our lower bound. The second one is a realistic batch use case. It is updated periodically, but there is a training cost. It is visualized using a gap between training data and evaluation. The third variant is a batch with zero training cost, and it's our upper bound that is unattainable in a real system unless we had infinite computational resources. The last one is a Lambda learner, and it has access to the same data as the upper bound because the cost of training is very low. It's actually negligible compared to the cost of training an offline batch model. This plot shows us how the performance of the models change with time. The batch model that is not updated degrades, while Lambda learner's performance is stable. Actually, this was surprising for us. Recall that Lambda learner uses approximation of the oldest data with a Gaussian prior, and we expected that the error associated with this approximation would accumulate over time and degrade the performance, but it did not happen, and this is a very encouraging result for us. Now let us take a look at the performance of our method and compare it to different batch baselines for different update frequencies and different costs of updates. There is nothing surprising in how the batch updates behave on this plot. As the update frequency decreases left to right, the performance of batch updates degrades as well. Also, batch updates with lower training cost perform better. You can see that the curves are nicely stacked on top of each other. Lambda learner, the solid green line, outperforms all batch variants except the upper bound, but it gets quite close. Another observation is that its performance is not impacted much by the frequency of updates. In real production system, Lambda learner outperformed the batch model that was updated every 6 hours, especially improving the performance for new advertisers, which was our original goal. There are also infrastructure wins. First of all, we think that the new data collection process is more reliable because it uses fewer processing steps and reduces the likelihood of engineering mistakes. Second of all, the data collection process is more efficient, and the data becomes available much faster, even for the offline batch models. So not just the nearline models benefit from the new process. Finally, the cost to serve is also improved dramatically because the training itself is less expensive and because we can skip some expensive offline transformation steps such as joins. Thank you everyone for attending to our virtual presentation, and please reach out to us if you have any questions.